Takagi. I have studied at Nara Women's University on aging and lifespan in the unicellular ciliate Paramecium, Zorimushi in Japanese. So therefore, I'm very pleased to share the presentation of Dr. Robert Arking, who is a leading scientist in our field, and he is also very famous for his book entitled The Biology of Aging. So this is also translated to Japanese. It's Rokan biology in Japanese. And this is based on his second edition, but the most recent one is this book. It is the third edition. Yeah. He is talking about why and how we age, and is that process modifiable? Dr. Arking.
Thank you for the introduction, Dr. Takagi. And I want to thank, as do the other speakers, I must thank Mr. Islam for organizing this interesting conference. The diversity is shown by Davidson, which I thought extraordinarily interesting. And we'll now look at the other end of the life cycle, so to speak. Okay, so we're going to talk about why and how we age, and is that process modifiable? It's 50,000 years ago. There's a 50,000-year-old grave in Iran that was discovered by anthropologists, and the body was laid upon a bed of wildflowers. You can tell it was done in the spring of the year. And that means our ancestors, presumably, were thinking about aging, life, and death, those serious questions back then. And so aging to that extent has been a central concern. And it's been accepted as an immutable fact of life. You must age. And that's largely still true, but not entirely true. So today I'd like to present some of the data leading to that conclusion. The technology is poised. We can manipulate aging in the lab. It turns out to be rather comparatively easy to do. And that technology is, as we speak, poised to move into human society. So these are forthcoming events. The goal of the talk, then, is to give you an integrated conceptual overview of aging over the lifespan. I love this subject, so I'd like to stroke each slide lovingly as we go through, but we cannot do that. We have to sort of truck through this, and I'll try and give you the overview as we do this. But that's what we want to do. Let's start. This is the past century. This is a survival curve of the United States data, but you see the same thing in any developed country. And this was lifespans over the past 100 years. So 1900, the survival is this line up here. In 1900, 20% of all children, this is a female graph, 20% of all children died by the age of 10. 25% were dead by the age of 30, and so forth and so on. You can see as we move up from 1900 to 1920, there's a big decrease in mortality, not due to medicine, due to public health. Sewer systems, public health, quarantine, things like that. And you can see those other movements up, and then later on in the middle of the century, increases in longevity this way, having to do with certainly antibiotics and certainly increasing values of cardiovascular medicine and so forth. And so there's an increase in the mean lifespan. But there's no increase in the maximum lifespan. Down over here. Even so, this increase in longevity is, I think, one of the greatest successes of the 20th century, not just in the US, but all developed countries. There is no good without life. The question now, and if you look at this, and you look at the life expectancy at birth from a best case country, so this early data is England starting in 1600. In Shakespeare's time, the life expectancy at birth was about 35 to 40 years, something on that order. And it sort of oscillated around about that. There clearly were, in his time, people who were age 60 or 70. He wrote The 7 Ages of Man, after all. But they were very rare. And so the point is, you start seeing an inflection in this point around 1800. They suddenly go above that, and it takes off like a straight line. This is probably the beginnings of the Industrial Revolution. Charles Dickens would be surprised to learn this, but it was increasing control of the environment. And what we have here is a series. This is not a line that describes the events in any one country, but the best case country. So it involves mostly Northern Europe and Japan over periods of time. and then we see the life expectancy increasing by 2000 to about 85. That turns out to be an increase of 1 month of life every 4 months lived, which is an extraordinary slope. And much of the question has been about, is it reasonable to believe this gain can continue in the future? And so this talk is to some extent an answer to that question. There's two conceptual models of aging. The medical model, which was dominant until recently, is that all deaths are due to disease. And that model assumes the existence of an aging program. This comes from Weissman's talk. He suggested that the frail elderly have to be removed in order so they will not outcompete the robust young. If you think about it, it's circular logic. It assumes what he wants to prove, and it's also totally illogical. How can a frail individual outcompete a robust one? But that's okay. It assumes the existence of an aging program. This is a testable thing. The biomedical model, which is the dominant view now, says disease and aging are different processes. Aging has an evolutionary basis, and there is no aging program. And this is a testable question, and I'll show you how we can test it. Each of us has faced the same question Francois-Jacob asked. We started out as a single cell. We created ourselves to be an organized adult of 1 to 2 trillion cells, highly organized, highly replicable. We can create ourselves, and yet we cannot maintain ourselves. This seems to be paradoxical. This can't be intelligent design. We fall apart. It just doesn't seem right. We asked the question, what answer can we give them? Jumping ahead to the answer, I'll go back to the process. We age not because we must age, not because there's a program, but because there's no reason not to age. And that's distressing to some people. I'm going to age and die for no damn reason at all. There's no cosmic thing in this. It seems sort of ridiculous, but this is where the biology leads us. There are several theories of aging. One put forth by Tom Kirkwood about 30 years ago called the disposable soma theory. Also the theory that says the chicken is the egg's way of making another egg. And this one says that all organisms have a finite amount of energy. And we can put that energy, apportion it either, broadly speaking, into somatic maintenance or into reproduction. You cannot maximize both functions because you only have a finite amount of energy. A kilocalorie put to one function detracts from the other. And so you have to make a choice as to what you're going to do. It turns out that and the assumption that Kirkwood made, and it developed from evolutionary theory, was that it costs less energy to reproduce than it does to live long. And since also the major gain, the point of evolution, is to maximize your Darwinian fitness, which means to maximize the number of genes you leave in the next generation, and clearly the choice should be that you should maximize your reproductive potential and inevitably minimize your somatic repairability. That was an assumption. We used some data a few years ago to test this system. That's what I'll show you here. This is fruit fly data. And in normal lived animals, which we'll go back to and talk about later, we look at and this is a curve involving calculations of the amount of energy used. I won't go through that. But at we reach a maximum peak of 1,150 eggs per female per lifetime. And at this point, these are the animals that have the maximum fitness. However, the animals that have the maximum longevity out here have a fitness that's less than half as good. Clearly, it makes sense for animals to maximize their fitness even if they will not live long. Okay? So our animals actually are following this disposable soma model, and this will guide our thoughts, I think. This is based on pre-existing models of some of the work of Modifiable and Hamilton and so forth. We've seen this quote before, and it's clearly very true. And the name of the game is to get copies of your genes into the next generation. Okay. We can use a poker analogy. You're an active player in this game of natural selection. And you're affected by natural selection only as long as you play the game. Once you fold your hand, you're a kibitzer. You're not at the poker table. You have no money on the table. You're standing on the side of the room watching the other players. It doesn't matter if you live or not. It only matters if you live while you're in the game, which means natural selection only works during the reproductive period, if that's the game. And your Darwinian fitness then is more important than your longevity. Let's look at some human data. This is some data from the US. Let's look at the right-hand side. And this is the age-specific mortality. In other words, what's the mortality rate of 6-year-olds, mortality rate of 8-year-olds, 10-year-olds, 52-year-olds, whatever. So it's age-specific mortality. And if you plot this on a semi-log plot, you get, in each of these dots is an actual data point. Neonates have a fairly high mortality. You can use neonatal mortality as an indicator then of the health of the society, because unhealthy societies have a higher rate and so forth. Anyway, it drops rapidly. Probably the mortality rate goes down to some minimum about 10 years, which I want to point out to you is just before puberty. Okay. And then there's this beep over here with the curve changes and goes back up. This bump over here is teenage boys doing silly forms of courtship behaviors to impress young ladies, usually involving cars. And when that's over, the survivors just simply have a straight line increase, and then it starts to curve down. More recent data shows that, in fact, the mortality rate goes down. If you were in the odd business of selling life insurance to 110-year-olds, you'd have to give them a lower premium than you would an 85-year-old. Now, it's a small market, but still. The idea that we begin to age from the time we're born sounds nice, but it's absolutely not true. If you define aging as the increased probability of dying in the next time period, then we are not aging as we're in this point, because the probability is decreasing. It only begins to increase over here, and it decreases about over here where it starts to drop down. So aging is only from about age 10 to about age 50, age 95 or so. And actually, natural selection is at its peak for other calculations, not inherent in here, we'll just tell you that. It's inherent, the maximum value of natural selection is just before puberty, and it reaches a minimum, disappears basically, at around 50. Why 50? It's 50 plus or minus 3 is the age of human menopause. And although males can sire children afterwards, and you see headlines in the paper from now and then that they do, still, some large number, 95% of all human reproduction is basically done before the age of 50. And so in effect, the odd male or two that reproduces out here is beyond the scope of natural selection. So natural selection is at a peak over here and has a minimum at 50, and it disappears. It's probably no coincidence that the first signs of age-related diseases start to show up in populations at about 55 to 60. There's no selective pressure to live longer. There's a mild one about a bottle conductor. And so this slope, if you just take the extension, the regression line through all the data, this is a Gompertz line, we now have an aging rate. This is a rate of aging. And you can express it as a simple line with two parameters, like as mx plus b. The slope is what we're after. This is the rate of aging. To understand this as a number, it's sort of odd, but Tuck-Finch came up with an idea that it's better. We can measure this, use a slope, refer to it as the mortality rate doubling time. In humans, that's 8 years. What does that mean? People in this room are of all different ages, but the probability of us going to sleep tonight and dying in our sleep is twice what it was back in 1999. That was the bad news. The good news is that the probability of our dying in our sleep tonight is only half of what it's going to be in 2015. And it doesn't matter what your age is. So what we can say then is that if this is the disproof of an aging program would be the ability to alter the slope of that line. And that we can do. So how many ways are there to alter normal aging in the lab? There's 3 ways, running through 2 of these fairly quickly. One is to, in fact, increase mean longevity. And you can see that there's an increase in mean longevity, but no increase in maximum. I don't have time to go into the details here. The second way is to increase maximum longevity, so there's a significant increase in maximum longevity at least, but no real significant increase in the mean lifespan of these fruit flies, I should say. And then there's a third way, which is a delayed onset of senescence. And here, very clearly, we have a large increase in mean lifespan, we have a large increase in maximum lifespan. This is what we'd like to do. I will come back and introduce these terms health span and senescence span in a few minutes. But this is clearly what we'd like to do in terms of increasing lifespan, increasing longevity. This is a Gompertz curves for that set of data. And so these are the controls, and these are the experimentals. These are just 2 independent replicates. And you can see that, in fact, there's a difference in the slope. In fact, the slope goes from 6 days, in this case, to about 9 days. That means that for these flies, we've slowed their aging rate by 50%. And that would mean, if we could do the same in humans, it would mean taking the age mortality doubling time from 8 years to 12 years. And since from going from 10 to 80 is about 8 doublings, well, no, it's about 12 doublings, that would mean you could go to 130 years. And simple to do that. The key to increasing longevity is to, in fact, decrease the age-specific mortality rate, decrease the slopes of these curves. So, the fact that we can do this shows there's no aging program in the sense it's defined with growth. And in fact, it demonstrates that the processes which control longevity are very plastic. How plastic, I ask? Well, let's look at this. This is, again, some of that same data. These RA is the name we give to our normal-lived animals. These are highly robust, outbred strains of fruit flies. The 2 lines are simply 2 independent replicates, just to show you repeatability. We have created from these by artificial selection long-lived lines called LA, and you see those. So there's a few aspects about this survival chart which I think are of interest. One is the fact that there's an inflection point over here. At day 28, the animals are very happy, thank you. At day 31 or 2, they're running downhill. What happened? Something happened in that short period of time, and there's an inflection point, something happened. What does happen there? And notice I did these RA animals. They were healthy, defined as having a survival rate above 10%, above 90%, for about 30 years. And then they go down this senescent period, as we define it, and they have a senescent period of about another 30 days. Half of their lifespan is spent in the senescent phase. If you look at the long-lived animals, which we used artificial selection and pushed this inflection point out to here, the question is, what happens here, and why? How did we get delayed? This is my reminder to tell my mnemonic. I'll tell you exactly why we did how it came about. It turns out that these animals, we didn't set up a mutant screen or impose a particular mechanism. We just said, we want you to live long, do it however you can. And so the flies had to sort out the mechanism. We did not impose it on them. And they did the following things. First, they have a very significant increase in their scavenging enzymes, catalase, xanthine dehydrogenase, superoxide, and this mutates for both cytoplasm and for mitochondria, glutathione peroxidase, other scavenger enzymes that soak up free radicals, which are destructive molecules in the cell and they cause a lot of damage. That's a specific increase. DNA repair genes are not upregulated. Glucose metabolizing genes are not upregulated. And that was not just an RNA thing. It went down to enzyme activities, transcriptional upshoot. We also know that these organisms also upregulated their small heat shock proteins, which are molecular chaperones and have a protective effect on the cell. Their oxidative damage in protein and in lipid, not surprisingly, fell to about 50% of the normal level. So they have very low damage levels. Their metabolism changed. The metabolic rate stayed the same. There's no difference in metabolic rate between normal and long-lived animals, but it's qualitatively different in these long-lived animals. For example, these long-lived animals are on the pentose shunt. There's some other changes in other enzyme activities. The other important point is that the mitochondria in these long-lived animals are very efficient. They're 20 to 40% more efficient, which means, and by that I mean they're generating 20 to 40% less free radicals. And because they're generating, essentially wasting less protons, the protons that are not wasted are there available now to make more ATP. And so, in effect, you've sealed the leaks on the engine. And this is where the extra energy comes from. You have more efficient mitochondria, you have lower levels of damage, you have to spend less money, less energy, money, same thing, on repair. And you're also, from the same calorie of food, you're getting more ATP molecules out because you're wasting less. And so the extra energy necessary to make these animals live longer and do the somatic maintenance comes from that increased mitochondrial efficiency. And that's something we're actively investigating now. Okay, and those are some of the mechanisms. The thing that's important, I think, in this case is that many of the experiments that are done in the field now, and they're excellent experiments, are to test a particular mutant or a particular pathway and see what effect one pathway has on longevity. And there are major effects. This has been useful. But these animals mobilize multiple pathways, and that may be a part of the fact of why they're so robust. And that may be a lesson or not, but that's what our animals do. We also were able to move this back and reverse the selection and get these back to normal. And the question is, why is it reversible? Why? Because everything I told you was increased in the normal, and the forward reselection was reversed in the reversal was decreased in the back selection. And by having a forward and reverse selection, you could discard all correlational changes. All these changes are therefore correlated with the longevity. This is a causal analysis. It's not just a correlation of data. That's fairly robust data. And so, and why is it reversible? Well, we just sort of vote, we're able to select for long life and make them turn down this scavenger activity, etc. There's another thing. We did biomarker analysis. And so these are various biomarkers of various types. In the RA animals, this biomarker X, I don't want to go into details, happened at this time. Now, the same thing happened in this animal, at an long-lived animal, at a much later time, but at a corresponding part of the senescent cycle, which lets us think that this is physiologically part. This biomarker is lost when you're at a certain level of physiological function, not at a certain level of chronological age. If that were the case, then this one should have been lost up here and so forth. And there's a string of them that happen in roughly the same place. This makes us think then that the senescent process is the same in normal and long-lived animals. Whatever's happening is the same, and that there's no qualitative difference there. We do see qualitative differences early in life. There's some behavioral traits which are lost early in life in the normal animals and much later in life in the long-lived animals. And this increased, the shift precedes or follows the increase in the oxidative stress resistance and so forth, which takes place quite early. So there's probably a causal relationship there. What we think then is that the long-lived animals have a health span that is the first 60 days at this point, and the 30-day senescent span. The 30-day extra longevity generated by the selection is entirely chunked into the health span. And so the extra lifespan is this group of animals right here, where they are, in fact, by definition, pretty healthy. That was the first difference over there. Okay. So health span and senescent span are two important points, and we'll come back to them. I think it's useful to divide the lifespan into these 2 points and what happens at the inflection point. We'll talk a bit about that. We give this name, we have to name things. So this is a delayed onset of senescence phenotype. And we'll refer to that as the delay in onset. What are the stimuli that induce the DAS phenotype? This is found not only in flies, but in other organisms. And now we'll shift to most mammalian systems. This were some analogies with humans. One is dietary restriction. And dietary restriction is a classic study. It was first brought up in the 30s. But the case here is that you cut your caloric intake such that you cut the calories, but your nutrients are maintained at a high level. So it's a nutrient-dense environment. And so here's a case. This is some very good data from Weinberg's lab. Animals, these are mice. These are couch potatoes. They can eat whatever they want. And they have a lifespan with a mean at about 28 months, and they're all gone by about 35 months. Cut their calories by 15%. You get an increase in mean and an increase in maximum lifespan. So this is a shift. This is delayed onset. There's also a corresponding shift in the apparent onset of senescence. If you go to this next one, which is a 50% cut, so this is animals have half the calories that those do. Then mean lifespan is at 45 or so, and the maximum is about 52, and you get this shift over. And so clearly then, these animals are delaying the onset of senescence. You see longevity. How does that happen? If you maintain, for example, cell structure, you don't have to be this is a skeletal muscle of a 1,200-day-old dietary restricted animal. This is a micrograph of a young animal on regular diet. You do not have to be a histologist, a pathologist to understand there's a huge difference in structure between those two. If function follows form, then clearly this muscle operates better than that one does. And so it maintains cell structure. In a human case, if the energy for this dietary restriction is thought to work by taking energy from reproduction, so to speak, and applying it to caloric restriction, dietary restricted mice are less frequent than normal mice, and so that holds up. In a human case, the question came up, is there enough energy in human reproduction to steal something, so to speak? And I've done papers out. We did an analysis of human reproduction. It cost, without going into details, 12.6 million kilocalories to take a human child in conception to the age of caloric self-sufficiency, which is 20 years of age, based on hunter-gatherer data That is equivalent to 25% of each parent's caloric intake for 20 years. And since calories and dollars are fungible, it's about 25% of each parent's disposable income for 20 years. Yes, there is enough energy available in reproduction that our body has physiologically set aside, so to speak, for us to tap into and use that. So this is a reasonable thing to do. What does caloric restriction do to a human? This is Roy Walford, a very well-known biogerontologist. He was an immunologist. He was also in the biosphere too, back in the 90s. This was about a 7 or 8 hectare closed system. 8 people went in for about 2 years, and they were to generate all their own food, their own oxygen, et cetera, et cetera. The calculations were off a bit, and they couldn't grow quite enough food, and they were eating about 1,700 or 1,800 calories a day while doing hard work. They were really working hard. And so this amounted to a caloric restriction experiment, and Roy was the one who said, well, it's not working, let's make lemonade out of this. And they turned it to a caloric restriction experiment. This is what he looked like during the course of that study. He was 54 kilograms, and then this is what he looked like a few months after he came out and back on a normal diet. You would say that he looks like he just got out of a prison camp, and this guy looks healthy. The physiology that I'll show you in a minute says that image on the left is a healthier man than the image on the right. Okay. Our concept of beauty is based on plumpness because in the past, fluctuating food sources meant that somebody who carried who was perhaps Rubenesque and had a little extra padding had a greater probability of surviving the next famine and carrying your child to fruition. And so there was this selective advance. Here's the effect of CR in humans. There are, in California, as it turns out, a group of people who have voluntarily put themselves onto caloric restriction and have made their medical records available. So here's some interesting, and this was published, here's some interesting data. Body fat goes down by 2/3, which you can see from the photograph. Triglycerides go down by 2/3. Most other numbers go down. The only ones that really goes up a bit is HDL cholesterol, which is actually a good thing. This is the most important one. The blood insulin level goes down by 80%. Insulin is a signal to the cells, and this goes down, and this will tie into some other data. The other thing that's interesting is this group of 3 proteins, TNF-alpha, C-reactive protein, GGF-beta, involved in inflammatory reactions. And so these are down by 50%. And so the caloric restricted individual has very low fat, increase in glycogen, although that's not mentioned here, and low insulin, with all that that's going to entail, and very low, non-existent levels of inflammatory response. What does this do? What do the genes, what does the caloric restriction do to the genes? And this is from mouse data, microarray data, so it's RNA, the differences in RNA expression in mice. And let's just look at that first case, CR on mouse muscle. These are 2 mice of the same age, one raised under avidum, normal food conditions, and one raised under caloric restriction, and so they're examined, they've been assayed, and this is some of the data. The normal aging mice have increased stress response. The genes that are involved in stress response are up. They have neuronal injury. The neuromuscular junction is really being damaged. And there's a decreased energy metabolism. These muscles, and you saw what the mouse muscle looked like before, are not repairing themselves because there's no energy to do that. If you look at the delayed aging ones on over here, in fact, you see they have an increased biosynthesis, increased protein turnover, increased energy metabolism. It turns out to be very healthy, important for muscle health, that in fact they are continuously regenerated, new molecules put in place, etc. And there's decreased macromolecular damage. You see a similar effect takes place in the mouse brain as well. And this data has been verified by other labs doing similar kind of experiments. So the dietary restrictions induces delayed onset. What about following your mother's advice and just leading a healthy lifestyle? Eat a vegetarian meal, no smoke, go out and exercise, that kind of thing. We can now look at this. We can compare Seventh-day Adventists who have a lifestyle that follows those precepts and compare them to the normal California population. And you see that people who are following this have a delayed onset of senescence, about 4 years or so, something of that order. They have an increase in mean lifespan, about 5, 6 years, somewhere like that. But there is no, and diet and exercise account for most of that increase in lifespan, increased levels. So you don't have to belong to this group in order to do that. You just have to do diet and exercise. But there's no increase in maximum lifespan. There's no decrease in the age-specific mortality rate. There's no slowing of age And so, although this is a good thing to do, it's not going to induce the delayed onset of senescence phenotype. There are clearly innate genetic differences, and which can do this. For example, there are fast and slow aging humans. Individuals at high risk for, which is a light color line for cardiovascular diseases, have a higher mortality. These are survival curves. They have a higher mortality than individuals who are not at high risk at all, or low risk groups. Just people on caloric restriction are at low risk for all kinds of cardiovascular diseases. The various markers are very low. Those people will live long simply because, if for no other reason, simply because they're not going to die early of cardiovascular diseases. We know that they'll live, and they're also at lower levels for cancer. So many of the disease risks go down. So they will live longer on a mean lifespan, even if their age-specific mortality doesn't go down, but it goes down in every other form, and there's no reason to expect it to happen in humans. So this is a negative case, and there are genetic defects that make these people die early. But centenarians and their relatives have a very strong genetic component, and some of them induce the delayed onset of senescence phenotype to some extent. There's a lot of heterogeneity. Again, we don't have time to go into that. But this is the important point, I think. We can also induce this by altering cell signaling patterns. Aging is, in fact, a cell-level phenomenon. And in fact, when you take high-caloric diet, what happens is you have a high amount of nutrition. It's sensed, of course, in your stomach, but also, more importantly, by your brain. There are then neurosecretory signals sent out through the body to every cell, and it alters the cell signaling in the manner I'll speak about right here. If you have a high-calorie diet, then the insulin-like signaling system is a protein that's similar to insulin, hence its name, insulin-like growth factor. The system is turned on, and when it's turned on, it activates growth genes, simultaneously represses stress resistance genes. The net result is an animal that is in the growth and reproductive mode, but it's aging because it's not activating stress resistant somatic maintenance. Caloric restricted diet works because this system is repressed, is turned off, therefore when it's off it represses the growth genes and activates stress resistance genes. You get an animal that has increased longevity, but it's not as fecund. View this as a two-pole switch that cannot turn on this set of lights or that set of lights, but it can turn both set of lights on together. Also understand this is a mechanistic, this is the mechanism underlying the disposable summer theory that you said you can maximize A or B, but not both together. You cannot turn on both sets of genes simultaneously. And this is the actual mechanism. In this case, this is a cartoon comparing the system in C. elegans, the little worm, which is a very useful laboratory model, in humans. And in fact, there was an exact molecular correspondence. 10 years ago, this molecule was identified as being part of the phosphoinositol 3 kinase. As soon as that was done by Gary Rufkin and got the sequence, everybody knew that PI3K was an integral member of the insulin-like signaling pathway from human physiology, and bang, we sort of cracked the code to what was going on in other studies to verify that. The point happens is there's just transcription factor. This is a protein that turns on other genes. If it's not activated, it stays in the cytoplasm, does not go into the nucleus. If it stays out here, it cannot turn on stress resistance genes, and the growth genes are activated. If it comes in here, it does reverse. And so that's basically the mechanism. The thought came up, how could you manipulate this to increase aging? Well, you could knock out this insulin-like protein, but if you do that, the animal dies. It's a necessary signal, so that's not good. You could knock out this receptor that it binds to, but without the receptor, you'll die. So the obvious answer that Holzenberger did was, suppose we make an animal that's heterozygous for a knockout mutant, and we reduce the number of receptors by 50%. If there's no upregulation of that, then we should be able to manipulate this. And so what we have is comparing lifespans of a normal mouse, female, and a mouse that has, it's heterozygous for a knockout mutation for the IGF-1 receptor, and so it's half the number of receptors. And you can see that these guys live longer, gaps rather. There's this delayed onset of senescence, increase in mean, increase in max. It doesn't work quite as well in the males for other reasons. So this low level, what the cell has done is it's been fooled into thinking that it has a low signal, because after all, only half the receptors at most are being saturated, And it interprets that as meaning that the insulin level is down at half, but it's really not. The animal's eating an ad-libitum diet. And so the cell it's possible to fool the cell. And that's an important point because an intervention to go so that you can still have a full dinner and fool your cells, it depends on this now. This is a quick summary just to show some of the pathways empirically known in Drosophila that will in fact induce this, create this delayed senescence phenotype. One I've talked about, this is the insulin signaling pathway. It goes through here, antagonistic relationship between reproduction and stress resistance. We won't talk about that anymore. There's another pathway next to it, target of rapamycin, the TOR pathway. This is also a nutrition sensing pathway, particularly involved in sensing amino acids. It also regulates cell size and cell number by independent manipulation. And so this can also alter, turn on various genes. This turns on this defoxo, as we now know can turn on this same transcription factor and work over here. Can also probably do it indirectly. It can activate this next gene called SIRT2 by an NAD-NADP. This is a signal that transmits information of the state of metabolism of the cell. And this can activate a cascade. This is actually a caloric restriction pathway, which activates, this is probably on the side, a gene called Arking, another one, the SIRT2, and it turns on maybe the fork head, but probably the defoxo pathway. And then it runs down the stem, which everything is going in, it gives longevity. Come back to that SIRT2 thing. There's a drug called, this next one is giving drugs. This is proof of principle for pharmaceutical intervention. This is a small molecule, 4-phenylbutyrate. Seymour Benzer's lab took this and fed it to flies. It turns out to be a histone deacetylase. They had a reason for doing it, we won't go into it. It turns out to be a histone deacetylase inhibitor, which means it opens up certain genes and activates them. It probably turns on the RPD3 and comes right down this same pathway. These animals also were induced to give a delayed onset of senescence phenotype and have the same kind of survival curve as our long-lived animals do. And so this is proof of principle for pharmaceutical intervention. This is a stress resistance pathway. Dirk Bowman did this, and that will also turn on the same gene. You see that receptor there and here, and probably in here as well. And so you can activate, if you activate stress resistance, you can in certain cases get this extended longevity. Increased mitochondrial efficiency, which is part of what we've done. We know that there's a tight relationship between caloric restriction, longevity, and the mitochondrial efficiency. Inefficient mitochondria do not allow an animal to express the caloric restriction response, and we're trying to understand that mechanism in some more detail. There is also anti-stress genes and repair genes you can add by genetic engineering, just stick them in. Now that approach is dying out because instead of putting in extra copies of genes, it's much more interesting to activate them and have them turn on. There's this SIRT2 gene is a topic of much research. It's the active resveratrol, which is the active ingredient in red wine that has documented health effects, which are presented in that particular paper, is being marketed well, we know it increases longevity. Increases by this delayed senescence phenotype. It's also been used by Sertris Pharmaceuticals and other biotech companies as the basis for intelligent drug design. Sertris Pharmaceuticals has filed to do a phase 1 clinical trial with their first marker, which is basically 8 times more efficient in activating that gene. The logic here is that you don't have to restrict your calories. You take this pill, you activate this, you turn on that whole thing, and you live on this way. And so we'll see how that works out. That may or may not work out, but the point is it is happening. There's another molecule called Juvenon, which doesn't turn on genes, but it does in fact, by standard means, increase mitochondrial efficiency, decrease ROS levels. But these two together, I think, illustrate the two classes of interventions. One will be a set of interventions that act upstream of a gene activation approach, and the other will be a class of interventions such as Juvenon, which will act downstream of the gene intervention approach. And so there'll be a couple of different classes that may come through, and we'll see how these work out. This is highly speculative. Okay, it's reasonable to ask that if there is no aging program, and if Darwinian fitness is the most important evolution, why should animals have systems in them that increase longevity, which seem to be contradictory. And that is because there's no point in reproducing at times when there's low food availability. In that case, your best strategy is to delay reproduction until the food supplies increase again. But in order to reproduce tomorrow, you have to be able to survive today, and so having these mechanisms to get through the tough times is in fact of selective value. Drugs, I told you about that. Change in signals, we have to do some trotting here. This is an interesting one. This has to do with muscle regeneration. Old animals cannot have a low ability to regenerate damaged muscles. And so this is a case where they took parabiosis, they took two mice and put them together with a shunt so that they had a common circulatory system. When they put two young animals together, they get a and did the regeneration test, they had a regeneration index of 20. When they put two old animals together, they got a regeneration index of 5, which is nothing. When they put an old and a young together, they got significant increases. So that the old animals are now able to regenerate their muscles at the same level, almost the same level as the young animals. That suggests there's something circulating in the blood, a signal. So they now went to another case of cells. They took young cells and covered them with sera taken from young animals. And you know it's a delta notch signaling system, so they got 50% of the cells with specific signaling response. Old animals, cells from old animals with old sera, they have half that level. You do the heterologous thing, young cells in age sera, you drop it down, put age cells in young sera, and you kick it up. And in fact, there's a problem in this case. The inability of animals to regenerate their muscles is partly a signals problem. It's not a hardware problem. Cells can do what it is, they're just not getting the signal. And so I think outcome of stem cell research may be a better indication of these signals and how to kick them up and do that sort of thing. Okay. Yes, right. I was too ambitious. Okay, but let me just simply say, senescence begins, if these are the genes that dietary restriction activates, these are the major Mendelian genes, it's not likely that senescence starts here with the major genes, it's likely it starts with the minor or modifier genes, and there's probably a fair amount of data here. And this is important because senescence, we all live healthy in the same way, but we all undergo senescence in an individual manner, and that needs to be accompanied, explained by some theory, at least in principle. Genes are an interaction network. You have spoke and hub genes, etc. These are the Mendelian or hub genes. These are hundreds of these things. The thing is that we think that the human disease genes, including age-related disease, are non-essential and are spoke genes, and they're not stable. That in fact, they do in fact break down in various ways. That the spoke modifier genes gradually lose their connectivity in a stochastic manner. And so senescence is a stochastic loss of function, not a programmed loss of function. That's an important lesson from this. We can get through here. Well, no, actually it shows one thing. It's interesting. In senescence, these are 75-year-old people. The fewer defects you have in different pathways, the better off you're going to be. These are survival curves. No defects in any pathways, defects in up to 5 pathways. So you would like to keep the stochastic damage down. Cellular processes in senescence, the automatic would stop up here, but you'd have other functions. You could have somatic mutations at the hub, which might give you cancer if you ran down this way. If you had just both things, you'd have loss of function at this point, loss of signal, loss of tissue function. So your choice in senescence is cancer or aging and degenerative diseases. This is a key thing. Lifespan is, you can view it as a health span in which you have longevity determinant mechanisms operate. This is gene dependent. High levels of sensitive homeostatic ability. You have a transition, which is event dependent. We get an altered balance of the cell's defenses due to some accumulated damage or loss of signal. In fact, the cell is shifting from a negative feedback system to a positive feedback system in terms of damage. Positive feedback systems are inherently unstable. And then you have a senescence span, which is stochastic. You get stochastic damage to the gene-protein networks. Things go to head from the hand barrel, and that's the end of that. That is one way, I think, to look at the health span. Looking at health span, transition, and senescence span. These then would be the events that take place at the inflection points that we mentioned earlier. Well, let me put this way. People think that this should not be done because of all these reasons. I think many of the critics are laboring under the false assumption that extra years can only be added to the senescence span. I think that demonstrated is the principle, but that's not true. Leon Cass, who was one of the opponents of delayed onset, said that death is a blessing. He writes gracefully, he also writes illogically. I've dealt with his criticisms elsewhere, and I won't go through it again, but his statements are really just personal preferences, no objective data behind them. I think much more important is Christine overall seeing that other things being equal, a long life is a better life. What about overpopulation? There's more people in the age of 65 and over in a developing world than there are in the underdeveloped world and the developed world. That's not a valid argument. Justice, well, what can we say about the effects of the longer health span? All we can really say, without writing a novel such as Rudy can, is that the society we're in today, that the year 2100 society, when these things are in play, would be as different from as our society now as we are from 1900. The other thing you can say is that there's no utopia. So nothing else, there'll be some problems. I think increasing the health span is like pouring sand to the top of the hourglass. The mechanisms are well known. They're susceptible to pharmaceutical intervention. It may be difficult. I mean, this first drug we're working on probably won't work, but that's okay. It's not going to be impossible. It will be controversial, for it lies on the intersection of biology and public policy. It will change the subject. Now, Schroeder asked, what is life? What gives me some consolation is that he did not answer that question in his book. So I can also not answer the question by modifying it. I can say, well, what is life for? And my answer is that life is to be lived, long and well. Thank you very much.
Thank you very much for your interesting talk, suggesting us how to promote our healthy lifespan. So now open to questions. Yeah, please.
Thank you very much. It is true that life is a very complicated hierarchical system, so as a whole, the organism is developing and evolving, but such evolution or developmental process, I believe, also occur within the system at any level. And my point is, I'd like to always answer to the question of what is aging. And I do think that aging can be interpreted in terms of intra-evolutionary process within the evolving organism. Do you think is this interpretation is plausible or not?
I don't think that it's a program, and I don't think there's an evolutionary selection. First of all, we senesce because of stochastic, because natural selection stops. It doesn't have to actually kill us, it just stops. And then we fall apart each in our own way. We have a mild selection pressure that keeps us alive to about age of 70, because if you last reproduce at 20, and it takes, at 50, and it takes 20 years to bring your child to caloric self-sufficiency, then you must live till that child is year 70 and that child is 20, and then it doesn't really matter.
But for instance,
but after that point, it's stochastic.
I see.
Well, there is no evidence to show that it is an evolutionary program. I noticed the evidence I gave you that it's not.
Yeah. Okay, but for instance, cancer can be interpreted by means of cellular evolution. Based on such interpretation, similar mechanism can be applied to other hierarchical level. And
well, there is competition with.
Really?
I'm sorry. There's competition in the body for cancer cells, within cancer cells, from cancer and normal cells, and so forth. And they can be looked at as competition at the cellular level. But the first oncogene mutation that occurs, it sets you on a certain path, some failure of a checkpoint mechanism. It's probably stochastic. It could be inherited mutation. But the mutation that sets you down that pathway is stochastic. It's not. There is no clock that says at 59 years turn on the cancer gene. Okay. You could make an argument the other way that says if your ability to detoxify materials decreases because your liver function is going down, then you may be indirectly programmed to have more mutagens in your system. But that's a very indirect. I mean, that's a good argument you can make, but it's indirect.
yeah, so if the cancer, in my point, if cancer can be interpreted in terms of cellular evolution, for instance, Alzheimer's disease, I think intracellular evolution.
There's some work that Phil Lanfield did, where essentially it's failure of cells in the, it's actually failure of stimulation. Someone will tell me if I'm going wrong or not. But failure of neural stimulation in the hippocampus circuit will in fact send a cell on a path. Lack of trophic stimulation will make a cell start to degenerate. That's not the same as selection per se, as an evolutionary bit. So, that book was written with the idea, based on the data, that it's not an evolutionary thing. If you think it is, then it's only useful as a doorstop. But there is this difference of opinion. But we could settle it by data, which I think eventually.
Thank you. Please.
Thanks, that was an encouraging talk. It's nice to know we may have more time than we expected. One step that I missed, maybe you said it and I just was spaced out, it was, you mentioned that there were some genetic pathways for enhancing delayed senescence in the fruit flies. Were these discovered more or less just by accident, by fooling around with the fruit flies, or from some kind of first principle?
Well, we made our fruit flies live longer, and then the question was, how are they doing it? We spent a lot of time, taking them apart and seeing that. We didn't, as soon as, and other people have done the same thing in the worm, and there's a mutant called Age1. Tom Johnson was trying to sequence that, so he could find the identity. No one could have the identity of his gene, just didn't know what he did. This was some years ago. And then, as I said, Gary Rufkin beat him by 2 months to sequence it. But once the sequence came out that it was a phosphoinositol kinase 3, and everybody knew that was a part of the insulin signaling system, and suddenly it made sense. Dietary restriction, to a certain extent, made sense. This was a system known to alter metabolism. And so they just, and then other systems came out. Once you knew it was insulin signaling, then you had a hook. You could look at other pathways, an independent body of data, for example, for the TOR system. And then there was an interaction between them, so that led to those sorts of things. So it was a bit of, so in one sense, sequencing the mutants that we had led to that.
So you sort of bred for longevity and then said, what was it that changed?
That's right.
That was this, and then you could sort of figure out why that might
Yeah,
have.
and work backwards once you had that done.
I see.
Fascinating talk. 2 questions. The first is, it sounds as though we'll be talking about pharmacogenomics because if each of us falls apart in his own way, then the medicines to which we're susceptible will be different.
Right.
Based on current knowledge, if you were asking questions about yourself or about any of us, which markers would you be looking for?
The single best marker for health is, for humans, would be respiratory. Your VO2, how much air can you inhale? It seems to have the highest correlation because it's a sum vector of the muscles, your lungs, your blood, etc. And the idea of using it or losing it applies to all organ systems. But VO2 is a very good one. The other thing that to look at would be to try and get your blood chemistry down like low, like this caloric restricted goods, low blood insulin.
But I actually meant DNA markers.
Oh, DNA markers. That's interesting. The centenarians, we have done some genetic analysis. Tom Pearl's group was looking at centenarians in New England, have a different marker than, I forgot his name, in New York, who's dealing with Ashkenazi Jews. And there's a third group, and it's again 3 different markers. And so it may be, and there's a strong hereditary thing, these are families that you track. It may be private mutations that are not widely spread outside. We'd like to know what they are, and that's another story.
My other question is, I might have missed this, what exactly do these SIR genes do chemically?
They are histone deacetylase inhibitors, so they open up, they inhibit the deacetylation of the DNA, of the histone. So the DNA is wrapped rather loosely and available for transcription. That drug that they gave to the flies, 5-phenylbutyrate, it does the same thing. It's actually, that drug's already approved for acne use by FDA. I don't know if you want to do that.
I'm very interested in your suggestion that the reason, sorry, your suggestion that the reason why caloric restriction delays senescence is because it's not worth breeding until you've got a mature food supply. Now that may be true for fruit flies, or may be true for animals, particular kind of life history. But in human beings, it's actually likely, we know of other evidence, that the forecast of what your diet and so on are going to be in the future isn't going to depend on what it is right now. It's going to depend on past events. So that, and we know, for example, that the maternal conditions can strongly bias a child to developing a particular strategy towards its own life history. Isn't it likely that in humans, a more effective way of increasing longevity would be manipulating the early embryonic environment, perhaps, of the child to give it false or different information about what its future held for it, rather than actually obtain the kind of thing which you're suggesting works for fruit flies, which is to day-by-day restrict or carry it.
That's actually a very, very good point. There's some evidence that this is happening already. This is Tuck Finch's data. And there's been this large decrease in infectious diseases and childhood diseases over the past 50 years or whatever. And what Tuck has shown is that people born after, who grew up when the diseases have been conquered, so to speak, are taller and healthier than the children, the cohorts that were exposed to the diseases. That's open to several interpretations, but one is that the children did not have to spend energy fighting infections, and didn't have the chronic inflammatory diseases that are really, really deleterious. And instead, that energy was used to build a physiological reserve early, maybe extra cells, extra good things, whatever. So they have. So it's essentially then was an early transfer of energy from fighting infection to somatic repair. Maintenance.
But
it's not quite what you're asking.
The paradox is that having a good maternal environment, which would predict good things to come in your life, should actually reduce your lifespan according to your model. And having bad conditions, which in other words, your weather forecast for what's going to happen down the line is going to be pretty bleak, is what's going to prolong your lifespan. So basically, if we want our kids to live longer, we should make sure that they have a pretty awful time during gestation.
No, that doesn't follow, because the Barker data doesn't show that. And so, in fact, the Barker data shows disparities between maternal nutrition and fetal trimester gives you defects of various sorts. But an optimal feeding, whatever that is, not fat, an optimal health of a mother would give you an optimally healthy child, and that's probably cool.
No, but you're saying that delayed senescence correlates with poor conditions for reproduction.
It's an evolutionary selective mechanism to get us past rough patches.
Yeah. So to say it again, if you trick the organism into thinking that the conditions are going to be poor, that's going to work, but you trick it into thinking the conditions are going to be good in the human case, that's actually going to reduce lifespan.
Yes.
So what I'm suggesting is that everything we think ought to work to increase lifespan, which is basically creating better conditions surrounding birth and what predictions of likely future benefits, are actually going to paradoxically reduce lifespan.
Not necessarily, because there's not a tight connection. I mean, other than extremes of bad health and good health, there's not a tight connection between development and adult longevity. Certainly not in the flies. And barring, we don't want to starve the children and pups or anything like that, but if they have decent health, there's not necessarily a correlation between those two. It's, I don't want to say there's no correlation, there's not a strong correlation.
There are some people who want to ask.
Two very brief questions, a technical question and a practical question. Technical question is, why does the IGF reduction not work so well for males? And the practical question is, does your research persuade you to live any differently in terms of diet, supplements, lifestyle, whatever?
Okay, for the first question, which is the easier one. In that particular case, it was probably because that was the mouse strain that they used for doing the cloning, when they transfer it out to a different strain, more robust, they get a better effect. You can see in other cases. So that's just something of that experiment, but not a general aspect. The other thing, have I changed my life knowing what I know? I work out at the gym a couple of times a week, try to eat a reasonable diet. That's more in the breach than not, but that's okay. But I console myself because people who go on diets, people who go on diets, not crazy diets, but just they go on a diet for 8 or 10 weeks and then stop. That in fact they have a lower mortality rate than people who never diet. And that is because they can turn on, it seems to be that they probably are turning on the early part of the gene cascade involved in caloric restriction, and that gives them partial protection. If you do that a couple of times a year, and you feel disgusted that you can't lose weight, which is a difficult thing to do, I know, but you are maybe giving yourselves a little boost along the way. And that's maybe, the other thing that mice do that I have not done is that you can take a mouse and feed it every other day. So you can gorge on Monday, starve on Tuesday, gorge on Wednesday, and you don't lose much weight, but you live long. And it may not be the actual long-term restriction, but in fact the hormesis effect, and that you're pumping out some resistance, so to speak.
Thank you. A little question on the last question. Okay, this later part of the life. You say in your written abstract here that you might have a healthy adult from the 20th to the 80th year instead of from the 20th to the 55th. That's a wonderful concept. But does it also mean that you have to have all those non-so-healthy 80s to 130 or so people seated in all these institutions where we have them today, where they are between 70 and 90?
This is a critical question. There's no evidence in the animal studies that this will increase the senescent phase. Okay, mice, the senescent phase sort of stays what it is, it's sort of separate, and that's what led to this three-part idea here. The other point is some data, again from Tucker Finch, I think, that suggests that, no, it's other data. Anyway, that over the years, as people have been getting healthier by a variety of measures, they also have fewer handicaps and activities of daily living, so they lose fewer of them. And so that suggests that, in fact, if you're healthy young, that even though you're senescent, you won't have all those terrible, you may not have as many. The other thing that should be noted is that it's not written that everybody will be, that this pill will do it for everybody. In fact, it's probably unrealistic to expect that. That has some problems in and of itself.
Well, that's reassuring. Thank you very much.
Thank you very much.